friends, in this video let us understand about NMR, Nuclear Magnetic Resonance Spectroscopy. What is NMR and why it is important? NMR is mostly used in organic chemistry to identify the structure of unknown molecules. We have come across many such spectroscopic techniques like UV visible, which deals with the electronic transition and excitation, and IR, which tells us what all the functional groups present in a given molecule. Coming to NMR, studying a molecule by NMR spectroscopy enables us to record differences in the magnetic properties of the various magnetic nuclei present and to deduce in large measure what the positions of these nuclei within the molecule. We can deduce how many different kinds of environments are there in the molecule and also which atoms are present in neighboring groups. Usually we can also measure how many atoms are present in each of these environments. When we look at the word NMR, N stands for nuclear. Somewhere it deals with the nucleus, and then M stands for magnetic. It deals with the magnetic field or magnet, and then comes the resonance. So this is not that resonance which we see in organic chemistry, that is hybrid structure or canonical structure. This comes from the physics background. Like when frequency or energy of two things matches, we say as resonance. So this is that resonance. In order to understand NMR spectroscopy, it is the most important for us to know about the atom. So this is our atom. It has nucleus and electrons. So we know these are protons and neutrons which are present in nucleus. There are many subatomic particles, but we are considering only proton and neutron here. So proton has positive charge, neutron is neutral, and the electron carries negative charge. So it's similar to Earth which rotate around itself, and also it revolve around the sun. So in the similar manner, electrons also has its own spin, and it also revolve around the nucleus. Let us consider electron spin. One is in clockwise direction and another is in anti-clockwise direction. So this spinning electron has angular momentum, which is given by under root of s into s plus 1 h by 2 pi. S is nothing. We all know that moving charges induces a magnetic field. So here also consider these electrons. These are charged particles, negatively charged particles. These are also moving, that is, spin is also a movement. Not only displacement, but spin is also considered as a motion. So this moving electron also induces a magnetic field. So that is given by, so here this is south and this is north, and here this is north and south. So here this moving electron induced a magnetic field. Like electron, nucleus also has its spin, so clockwise and anti-clockwise. So this is also a charged particle, that is proton and neutron. So proton is positively charged, so moving charge induces a magnetic field. So here this is north and this is south, and for this moving charge, the angular momentum is given by under root of I into I plus 1 h by 2 pi. So here I is nothing but nucleus spin quantum number. So we differentiate electron spin and nucleus spin. Electron spin has a fixed value, that is half, but nucleus doesn't have a fixed quantum value. because the composition of nucleus varies from atom to atom, that is number of proton and neutron present is not same for all atoms, so I value also changes. So NMR is the most powerful tool available for determining the structure of organic compound. This technique relies on the ability of atomic nuclei to behave like small magnet. So we have seen that it has a induced magnetic moment, so it behaves like a small magnet, that is it has north and south pole, and align themselves with an external magnetic field. It can align itself along the direction of the magnetic field, or it can oppose the applied magnetic field. So we will see about this character later on. When irradiated with a radio frequency signal, the nuclei in a molecule can change from being aligned with the magnetic field to being opposed to it. The energy frequency at which this occurs can be measured and is displayed as an NMR spectra. The most common nuclei observed using this technique are proton and carbon 13. So we can use some other elements also. So only those nuclei which have either odd mass, odd number, or odd, either one must be odd number or mass number, they are only NMR active. So if it has even number of proton and even number of mass number, then that is NMR inactive. So that is given. All nuclei possess either half integral or full integral spin quantum number. So they have I is equal to n or n by 2, that is quantum number. Allowed spin state will be 2i plus 1. If I is equal to 0, then the spin state is 1. If I is equal to 2, then it will be 5. If I is equal to half, then it will be 2. So here is the list of compound with spin quantum number and allowed spin state. So from here, this mass and atomic number, we can easily identify which are the elements that are NMR inactive. So odd, either one should be odd. So here even. So carbon 12 is inactive, and then comes here oxygen 18 and oxygen 16, and then sulfur 32. These all have spin quantum number 0. These are NMR inactive. This is the principle behind NMR. Like electron, the nuclei of certain atoms or their isotope possess intrinsic property of spinning along their axis. These spinning nuclei, being charged, generate a magnetic moment along the axis of spin. Thus nuclei behave as tiny bar magnets. So we can see from this that not all atoms possess such magnetic properties. They differ from atom to atom. So let us come to that point which I mentioned about aligning and opposing with respect to the applied magnetic field. So this is the applied magnetic field, and this is our point of interest, that is a tiny bar magnet. When we place this bar magnet in a strong magnetic field, there are two possibilities. One that is aligned with the magnetic field, and the other which is in opposite to that of the applied magnetic field. So this has the lowest energy, but it is the most stable, and this is the opposite, has highest energy and it is unstable. So in the similar way, when we place a nucleus in a magnetic field, it also behave in a similar way. Either it can align itself with the magnetic field, or it oppose with respect to applied magnetic field. Initially, the particles are in random motion, that is, their spin is not in a specific manner. But when the magnetic field is applied, then there are two possibilities. One is alpha spin state and the other is beta spin state. So this is with respect to magnetic field and this is opposed to magnetic field. So the energy difference between the alpha and beta state is given as delta E equal to gamma h by 2 pi b naught. So this is gyromagnetic ratio and this is the magnetic moment.